Hello interwebs, welcome to Let's Fix Computers. Sorry, I just started doing the intro and was just like, where's my multimeter? Okay, I found the multimeter, it's alright. I've got a HP Omen here. This is a mail-in repair. Whenever I get one of these big old gaming laptops in for repair, I'm immediately like, oh no, it's probably going to be a high side short with a dead CPU in it. And I'll explain a bit more what that means in a moment. However, I've had a preliminary look at this one, and I think it's actually fixable, so here we go. The customer has already had a quick look at this one, so when it came to me, the screws were already removed from the bottom, and if I just take the bottom panel off, the battery was disconnected, and the display cable here was also disconnected. So I grabbed my multimeter and just did some initial probing, and where I'm looking for when I do that probing to sort of start figuring out if I think I've got a viable repair or not, is I want to check the main rail. So I put my multimeter into resistance mode, and I'm going to put my black probe on a screw hole. I'll just pick this one down here near the battery, and I'm looking for somewhere where I can measure the main power rail. And to find the main power rail, I'm looking for large components that will be on the main power rail. So we've got big capacitors here. Those will probably be on the main power rail. These are big 25-volt electrolytic capacitors. The other giveaway is to go straight to the CPU or GPU VRMs. However, those are hidden under the heatsink because it's a big gaming laptop. So no easy visual exposure to those from here. But also I noticed up here we've got a fuse going toward the display connector. That's going to be the backlight fuse, and that will be on the main power rail because the display backlight is generally powered directly off the main power rail. So if I just stab the side of that, and wah, we have 0.1 ohms, big short. And if I just check the other side of it as well, same deal. So this fuse has not blown, but it is on a shorted rail. Now, this doesn't mean that the backlight is the problem. It's just the backlight is on the main power rail, and that's where a fault is. In a recent video on a Dell that I did, I showed how once you have a main rail short, you've got a whole network of stuff that will appear shorted. And that doesn't, measuring it at a certain point doesn't mean you're close to the fault. It just means that you're looking at the network that is shorted to ground. So we can also check these capacitors that I pointed out. So if I just measure the side of those, so again we can see that is short, and the other side, I think the stripe indicates negative on an electrolytic. Yeah, it does. Yeah, so shorted on both sides, and again on this one down here, same deal. That's going to be shorted, which it is. So we've got a main rail short. Now I'm excited about this one because it's 0.1 ohms. It's dead short. It is as low as we can go. That 0.1 ohms, that's resistance in the probing and stuff like that. So, you're not going to get much lower than that. Now, if I saw, say, 4 ohms or 3 ohms or something like that, or maybe like, 0.7 ohms, then I would be really, really worried that we have a high side short. And what I mean by that is the CPU and the GPU will have either MOSFETs or power stages providing a power supply from the main power rail into their core voltage, into the core voltage of the CPU and GPU. And those MOSFETs are part of a buck regulator circuit, and that has a high side and a low side MOSFET. So the high side MOSFET is switching high voltage down to low voltage through the regulator. And the low side MOSFET is alternating with that, and between the two of them, they step down power. Now, if the high side MOSFET fails for some reason, it will typically fail short. And by that, I mean it will fail shorted through. Now, when you have a short, that doesn't necessarily mean you are shorted to ground. It just means that a component has shorted through. Now, if that component is, say, a capacitor that connects to ground, you're shorted through the capacitor and down to ground. So you get short to ground. However, a MOSFET doesn't connect to ground. So if a MOSFET fails, you have a short through the MOSFET into whatever it's powering. Now, if that is your CPU, what you'll see is a short from the main power rail through to the CPU. And that means that 20 volts from the main power rail has gone directly into the CPU. And that small amount of resistance that you see, that sort of, say, 3 or 4 ohms, depending on which CPU it is or which GPU it is, that's the resistance through that silicon chip. So when you see that low resistance but not zero, that's bad. That means you've probably got a high side short, and that probably means the CPU or the GPU is dead. Not always, but most of the time. It's very, very common fault on gaming laptops because they have high power CPUs and GPUs in them. And it's one of the reasons why most repair shops dread fixing laptops like these, because so often it's a high side short into the CPU. There's nothing you can do about it. Maybe you can find a replacement motherboard, maybe you can't, but usually you end up having to say to the customer, sorry, your £1,500 laptop is dead, go buy another one. And it sucks. So, with that proviso in mind, I think we've got a winner here. So, I've waffled long enough. Wow, we're nearly 7 minutes into the video and I haven't rolled the intro. So, here's the intro, everyone. And I'm going to start taking the heatsink and the motherboard out of this laptop. This video is sponsored by FlexiSpot. FlexiSpot are a leading provider of standing desks, office chairs, furniture, and much more. Their E6 series features a dual motor design with a 3-stage lift system that has fast adjustment while remaining quiet and smooth, from 60 all the way up to 125 centimeters high, suitable for any use case. The control panel features custom height presets as well as USB charging ports and an anti-collision system to stop the desk if something is blocking it. The frame is available in black or white with a variety of wood finishes, providing a stable and durable one-piece desktop. I've had a FlexiSpot at work for years now, and it's been an invaluable part in improving my work ergonomics. This was followed by my E7 4-leg desk at home that has the power to lift even my heavy gaming setup. I can personally recommend these desks for anyone wanting to improve their desk comfort with the ability to switch between sitting or standing throughout the day. With their huge range of size and lift capacities, there's a FlexiSpot for any setup. Learn more in the link down below. Are we ready? I think we're ready. Who's holding on? No one. Okay, there we go. Right, visual inspection of the motherboard. No explosions on the back. And not seeing any explosions on the top at first blush. So let's briefly have a look at this board and see how the power gets to the CPU and the GPU. So we start out at the DC jack, which is this cable here. So that sits up there and it plugs in here. So our power comes in here, goes down onto the board. So we've got this area down here immediately at the DC jack. Let's come under the microscope and take a look at there and see how it's set up. So we come into the DC jack and we've got all of our positive pins here and then our negative pins here. And the first thing we have is across the positive and negative, we have a TVS diode. So that's a transient voltage suppression diode. This guy's here to protect from static shocks, lightning strikes, reverse voltage, just gross problems with the power. By default, it is a diode that is wired in reverse and it does nothing. But if there is a massive overvoltage coming in, then this guy will break down and conduct the voltage directly through to the negative. so it'll bridge out the input. Likewise, if the power was coming in the wrong direction, so the positive was connected to negative, it would conduct in reverse up to the other side, again bridging out the input. So this guy just does nothing unless there's a massive power fault that would otherwise damage the laptop. So just for posterity, we'll just check that there's no short circuits here. I'm not expecting there to be one, but we can check it. So I'll just put my black probe on the negative side, my red probe on the positive. And as you can see, we've got a crap ton of resistance there. We've got like 20 mega ohms. It's settling, but whatever. Lots and lots of resistance. So as soon as we've gotten past here, we immediately hit these two MOSFETs. So this is the first part of our DC in MOSFETs. On smaller laptops, you would have two MOSFETs in series. This one, the first MOSFET, there's two of them. You can see these are in parallel. You can see this big blob trace here. These guys are in parallel across to here. And they're in parallel just purely for current handling, basically. This is a high-power laptop. The power supply for this laptop, I'm going to get it just to show you guys because it should be illegal. Here is the charger for this laptop. Like, it's the size of my hand. This is a 330-watt power supply for a laptop. Woo, lad. That's why we have two DC in MOSFETs. So we go through these chonkers, and then immediately we're going into this big network of vias. We're going down through the board. So let's flip the board over and see what's on the other side. And when we get to the other side, we come up through the board and we go through the second of our DC in MOSFETs. You'll notice that there is a pad where they could have doubled up on these as well, but apparently they decided that that wasn't necessary. So yeah, I don't know the reasons why, but whatever. Immediately, that doesn't look good. That might be our problem right there. That looks sketchy as heck. So we're gonna take a real close look at that guy. Anyway, so we come up through here. We go through the second stage of the DC in MOSFETs, and then we go through a current sense resistor. So remember from the previous videos, we've got a big flat resistor package here. And look, there's our two little sense wires coming off of it. That's how we know it's a current sense resistor. Big flat square, probably with a resistance number written on it, and two sense pins coming off. One of them will go to each end, and that's going to go all the way back to our power management chip. All the way, wow, it's going cross country. There we go, it comes all the way back to this fella. So there's our power management chip. So this guy's watching that current sense resistor to see how much power the laptop is drawing through the charger. So, and then once we go through the current sense resistor, we now become this big trace here. And when we look closer, you can see that that trace is then just being this huge artery going through the board. So that's our main power rail. And we can follow that over to this section. This is where we go into the power area for the GPU. Here's our GPU power supply. And then if we follow it up in this direction, it goes up to here and it becomes the CPU power supply up here. And then it's going to go to other places on the board as well to power other secondary power supplies. So if we measure this current sense resistor, we're going to find that that's shorted to ground. So let's just check that for posterity. And as you can see, there's our short circuit there. And if we roll back to here, before the DC in MOSFET, we're not shorted anymore. So our short circuit starts here and is somewhere on the main power rail. It might be that guy, because I don't know, maybe that's just some dirt. It could be nothing. It might be that capacitor, we don't know. Could be only one of those, it might be something somewhere else, who knows. So when we follow it up to the top of the motherboard where the CPU power supply is, we come up to the top and we hit, here's that fuse that I was measuring. So I'll show you the close-up. So here we can see the main power rail coming into this fuse that goes into the display connector. So that's our backlight power fuse. That's where I measured our short circuit. However, in addition to that, it's also going into these MOSFETs here. So we'll find that the inputs to all of these are all shorted as well. So we'll just check that for good measure. I'll put my black probe on a screw hole, and let's just probe around here. So if we check, let's see, if we check these inputs here, there we go, there's 0.1 ohms. And now if we go a bit further on, once we go through these MOSFETs and we come out here, now you see we have 9.6 ohms. So that's not our dead short, but remember what I was saying about a high side short. If we had a dead high side MOSFET, we would be seeing that 9.6 ohms on the main power rail. If one of these MOSFETs had failed and just become a short through, then what we would find is we would have a path through one of these MOSFETs and through the CPU. And we would be seeing that 9.6 ohms everywhere on the main power rail. However, because we're seeing 0 on the main power rail, there's our 0.1, and we're seeing 9.6 on the, and we're seeing 9.6 after the CPU MOSFETs, that tells us that these guys are all okay. So we know that our CPU is okay. We can check the GPU as well. However, GPUs are really, really low resistance, so I don't know if we're going to see something useful here, but let's have a look for funsies. If we come over here, so we've got this huge bank of inductors and VRMs here. This must be a massive GPU. I'm curious as to what that is. Let's have a look. So that chip is a GN20 E3A1. Let's Google that. Really? It's a 3060. What CPU does this have? How does this thing justify having a 330 watt power supply? Nah, I'm not sure what CPU that is. I'm not sure which one of those numbers is going to help me out. Oh well. Well, apparently this GPU has a massive power budget available to it. Maybe it's very, very close to a desktop GPU in performance. Anyway, so let's go over to here. So this big electrolytic capacitor, this will be on the main power rail because it's a huge capacitor, 25 volts. So it's rated for 25 volts because it's sitting on a 20 volt power rail. And this capacitor is on the main power rail and is shorted. So there's our short circuit. So if we go through one of these power stages covered in goop, we go through the inductor, and this will be our GPU core resistance. And as you can see, our GPU core resistance is 0.27, 0.25. It's really low, but it's not the same as what we're seeing over here. 0.012. Sorry, 0.10, 0.12. So again, even though this is really low resistance going into the GPU, it's not the same as the short circuit we're seeing on the main power rail. That's how we know that we don't have a high side short. So this also means that we're basically good to inject power at this point, because if we inject power onto the main power rail, it's not going to go directly into either of the super sensitive chips. So we're not going to damage anything. So that being the case, I'm just going to immediately turn on the power supply and stab this thing. So let's go over our procedure now. We know we have a short circuit on the main power rail of this motherboard. So the main power rail, something on that rail has shorted out and is bridging the whole rail down to ground, so it cannot power up. So it's going to be a component somewhere on here, but we don't know where. You know, it could be one of these tiny little capacitors that we were looking at near the DC in MOSFETs. We found a bit that looked kind of dodgy there. You know, it was a bit darkened, a bit blackened. You know, it could be one of those guys. But equally, it could be one of these electrolytics. It could be one of the tiny little capacitors on these VRMs. It could be one of the little capacitors up here. It could be one of the capacitors around the GPU VRMs. We don't know. Because all of them are connected to ground in parallel, it could be any one of them. I've seen a comment popping up on a couple of my videos from a couple of different people recently saying, why can't you just measure each one of the capacitors to see which one it is? So in order to measure resistance, the multimeter is passing a small amount of power between the probes. And by measuring the drop in power, the multimeter can calculate the resistance between the probes. Now, if we measure across this shorted capacitor, then we see 0 because it's just a wire. So there's no resistance through it, and we get a 0 reading on the multimeter. However, if we measure this capacitor over here, the reason why we still see 0 is that the power going between the probes isn't going to try and go through this capacitor. It's going to go around through the shorted capacitor instead. So for this reason, everything on this rail is going to read as 0, because wherever we measure, it's just going to find a path through the shorted component. And the problem is we don't know which one of them is shorted. So this is why we get stuck and we have to use power injection. So instead, we're going to apply 2 different probes that are coming from a power supply, and instead of applying a small amount of power between the probes, we're going to apply a large amount of power between the probes. And that's going to cause the shorted component to get hot, because the shorted component is not supposed to pass this amount of current. So because it gets hot, we can then spot it using our thermal camera, and thus we find out which capacitor is shorted. So I'm going to hook up this crocodile clip to a ground point here on this screw hole. I'm going to set my power supply to 1 volt and 2 amps, and I'm going to get my Infrared P2 Pro thermal camera on my phone here. So now I'm going to probe the motherboard with my positive probe, and I'm going to stab the backlight fuse because it's a nice big device. It's easy to stab that with the probe and not miss. So I'm just going to set this at an angle just so I can see the board and wave my camera around. And what's going to happen is that the voltage will drop down because we're in a short circuit. So the potential difference between my black probe and my red probe will be basically nothing, and we'll just start passing up to 2 amps. So let's just do that now. Bam. So as you can see, the power supply has dropped into a short circuit at 2 amps. And if I look around, there's my hand. Lots of reflections, but not seeing anything get hot. Let's check the other side of the board. Did I call it? Is it going to be these guys over here? So on this side, I'll just stab the current sense resistor because, again, that's on the main power rail. Here we go. Got some reflections. Those orange spots you're seeing. All right, let's flip over and look again. So if we don't see it this time, we're going to go to a higher amperage. What might be happening here is whatever is shorted is sitting on a ground plane or as a large component and is able to soak up 2 amps without overheating. I'll give you a better view when I find something. Wow, no kidding. Yeah, something is just tanking that. Okay, let's go to 3 amps. Whatever this thing is, it's beefy if it's literally invisible. It's 3 amps. Okay, so at 3 amps now, we're starting to see residual heat building up on the board over here. Let's flip it over and see what's on the other side. There it is. Yeah, I was right. Okay. There's our orange spot. Okay, I'm going to bring in for a close-up so you guys can see that. So the area you're looking at now is the DC in MOSFETs and the current sense resistor. So there's our DC in MOSFET, there's the current sense resistor, and here's those capacitors that I pointed out. That was the one that I thought might have been it. Let's see which one is actually lighting up. There we go.
Now that guy's tanking 3 amps, which is a lot for a capacitor of that size. So how is it only getting that hot at 3 amps? This thing should be on fire with that current level. Well, let's take a closer look at that under the microscope. So the simple answer as to why this guy seemed to be capable of tanking so much heat without showing up on the thermal camera is that on the left side, it's sitting on the huge main DC rail power in. So this is a big, heavy power plane. And on the other side, it's got a big, heavy ground plane going to the negative pins of the DC in jack. So basically, it's got a heat sink. By having 2 massive power traces on each side, the positive DC in trace and the negative DC trace, it's basically got a heat sink on both sides of it. So while we're dumping current into that capacitor, it's dissipating the heat into the circuit board, which makes it very difficult to catch. This one would have been really difficult to find without a thermal camera, without just completely cranking up the amperage. All right, so we called it straight away, but there was no guarantee that one was going to be it. So let's take that off the board and see if our short circuit disappears. So I'm coming in with my secure HT140 hot tweezers here. So hot air is also completely acceptable here, but again, because we've got these big power planes, this is going to put up a bit of a fight because there's going to be a lot of heat soak here. So I'm just going to wet these joins. Oh, I'm at 300 degrees. That's not going to do me much good. Right, there we go. There's 380 degrees. We should have a bit more luck now. So once again, I'm just going to wet these joins. There's one side. There's the other side. Now we should just be able to just grab that off. And it is fighting, but I expected it to. Come on, wiggle, wiggle. 400 degrees. There we go. So with that capacitor removed, we'll check our resistance to ground at the DC in area again. So I'll just check that current sense resistor. And as you can see, we now have high resistance. 7,500 ohms. And once again, like if I go up and we'll just check the backlight fuse again. We'll check that guy. There we go, and again, 7.5K. Cool. So yeah, not massive resistance considering how big a power rail this is, but it's still in the kilo ohms range, which is the important thing. It's not 0. So next question is, we need to know what value this capacitor is. There's the guy there that we just removed, and you know, just for posterity, let's just measure him, and we'll find that he's at 0. I shall anthropomorphize this capacitor by calling it he. This boy. As you can see, that capacitor is dead short. It's just a wire. And it's looking deeply unhealthy now because it's been power injected and then ripped off of the board. So yeah, it's kill. It's cactus. So what I'll do now is I'll take off one of the other ones next door to it and we'll measure that to see what its rating is. God, this one's putting up a fight as well. Come on. There we go. So I've just deliberately knocked that sideways just because it makes it easier to measure. Now I'll put my multimeter up into the capacitance mode. So we're now measuring farads. And we get... and that is reading just under 25 microfarads. So that's going to be a 22 microfarad capacitor, because 22 is the nearest denomination there. The two common types that you get around here will be 10 microfarads or 22 microfarad capacitors. So these are 22 microfarad. So, and these will be 0805 in size, I think. I never remember. However, also there's a couple of different sizes, but that 08 something is the important thing. And they'll be rated for about 25 volts because they're on a 25 volt rail. Small ceramic capacitors like this generally have a fairly high voltage rating, but you do need to watch out when you get down into the smaller sizes. When you start seeing 06, 04 parts, that's when you might find that for like 10 or 22 microfarad capacitors in 06, 04, you might find they're only rated for like 15 volts or something like that, or whatever the nearest voltage denomination is. But for these 0805, I think it is, they'll be rated for 25 volts, so we'll be fine. Right, so I will bust out one of my spare caps. Here is my string of spare 22 mic capacitors. And if you're wondering what capacitors to buy, just buying a bunch of 22 mic and a bunch of 10 microfarad capacitors is a pretty good place to start. That's most of the ones that you're going to be replacing. And if in doubt, buy one of the cheap Chinese selection packs of capacitors and resistors in 0805 for the capacitors and 0604 for the resistors. And that'll cover most of the bases for stuff that you're likely to come across. So let's put some flux on the board, and we're going to flow those guys back on. Lots. All right. Put you back into place. Wow. Immediately gets stuck to the board. What the heck? There we go. I'll tidy that up with the main iron in a minute. Turn the board around for easier access. God, oh my days. This ground plane is like an anvil. No wonder this thing was sucking back heat. Oh. The hot tweezers are struggling on this one. There we go. All right, that's on. We'll touch it up with the main iron. My general use Akeson soldering iron is a 90 watt boy, and it's got a bit more grunt behind it. Bigger tip. There we go. We can just tidy up those joins a little bit. That'll do. Bit too much solder on those, but it's good enough. All right. And let's clean up that flux that I've just burnt on there. There we go. That's good enough. I have too many things on my desk this week. Just like too many objects. There's a stack of laptops on my left, which means the pile of stuff that I've taken out of this HP has nowhere to go, so it's just there. Working myself into a corner here. Let's get this guy fitted again, and we'll see if it all works, which it should do. There we go. There's a few missing screws from this, and like we don't have an SSD in there, and I'm pretty sure there should be more RAM than that. But this is what the customer supplied me with. That's enough for us to switch it on and check that it works, though. So we'll just put the back cover on, and we'll do a power on test and see how we go. Right. Plug the charger in, and we've got a light on the charger. Bam. Got a power light. I hear fans. And show me that HP logo. Will probably be an Omen logo, but whatever. It might power cycle a couple of times because it's probably got a RAM train. Oh, there we go. CMOS reset. Cool. And now we should crash into BIOS because there's no boot device. But the fact that we just got that far means we're all good. So, it's the same old story. Lucky escape though. Like I say, with these gaming laptops, you don't always get lucky. More often than not, it is a high side short when you get power issues on gaming laptops like this, which is why I just don't like them and I don't like fixing them because they don't always have a happy end like this one. But lucky escape and interesting example of the same old fault that we always see, but this time on something that's a lot bigger and beefier. So yeah, that capacitor was a little bit harder to notice because it was sitting on big power planes that soak up all the heat you're trying to pump in with your power supply, making them harder to spot and harder to remove as well. It's possible that there was a lot of warmth in that area because that was DC in, and again, the absolutely ridiculous 330 watt power supply on this thing means that there's just a lot of power in a small space in this laptop. Not the highest power laptop in the world, but it's pretty far up there. I think the only way you go higher than this is there are a couple of weird ass Acer Predators with like 2 power supplies or something ridiculous like that. Anyway, thank you everyone for watching. Thanks for tuning in. Thanks as always to my patrons, my YouTube channel members, and my Twitch subscribers. And I'll see you all in the next video. Bye for now.